that, we're going to go through a series of 5 presentations, just like we did earlier for missions. These are focused specifically, though, on technologies that we might try to consider of trying to apply to future missions. And we're going to start off with Jacqueline. As she's coming up here, all the people who are speaking next, please keep your talk to about 5 minutes or so if you can. Also, for those of you who presented for your breakout groups, at some point in time, soon, it doesn't have to be now, but soon, if you could write up some brief notes, Butler already got some from you, just summarizing what you talked about. We try to take notes, but it'd be great to hear directly from you because you know better within your groups. Just send them to me, and then we'll compile them all. And now, Jacqueline. This is for laser pointing. That's right here.
Okay, so I am going to talk about autonomy in the context of distributed spacecraft mission, or DSM for short, and particularly for designing intelligent intelligent and collaborative constellations. So although DSMs exist for a little while, for example, for multi-mission like the A-Train, or more recently Cygnus or MMS, and there has also been a lot of talks, like Mike was talking this morning, about sensor webs. There has not been yet a DSM that is truly collaborative with inter-spacecraft communication. And so recently, with a renewed interest in DSM, especially due to all the different the small sats and the CubeSats, and also the miniaturization of components and instruments. At Goddard, we have conducted some studies, and in particular, we have interviewed 55 scientists at Goddard, and we got a lot of ideas and potential mission concepts about DSM. But at the same time, we also got a lot of questions about what exactly are intelligent constellations. And we got questions, and this echoes what Larry was talking about this morning, about what is really an intelligent constellations. Why would we want to do intelligent and collaborative constellations? And why don't we just want to send all the data on the ground? And why do we want autonomy on board? So this presentation was really trying to look at to respond to these kind of questions. First of all, trying to define what is an intelligent and collaborative constellation. Then trying to see under which conditions do we want autonomy and an intelligent constellation. And finally, what are the technologies that can enable this type of DSM? So I will probably not repeat everything that is on the slides, because I realize that everything that is on the slide has probably been said in one form or another since this morning. But for example, intelligence, the goal of intelligence for a constellation is to use the result of onboard processing to target or reconfigure other spacecraft or other sensors in the constellation. And as was said before, the intelligence is made of several components, and I will not go into these components. But one other thing is to look also at what do we call an intelligent constellation. There are different gray level in terms of intelligence, and where do we put the threshold to say that it is an intelligent DSM if part of it is controlled from the ground and part of it is done autonomously on board. And finally, what is collaborative or cooperative? And the main goal here is to optimize the science return by taking advantage of the different sensors that can have different capabilities or different viewpoints. And it's really by doing collaboration and interactive collaboration between spacecraft that we can really get the full potential of a constellation. So the next part is when does it really make sense for a constellation to be fully autonomous? And this is really, there are different threads, and we can look at different things. The first thing is what are the events of interest that we are looking at, and how do we characterize these events of interest? And it's really the very first goal is to observe events that are unpredictable and look at them in terms of their location, their start time, their duration time, and their change throughout the duration time. And it makes sense to have a constellation that is fully autonomous when we look at the trade between the communication time, as was said before, the communication time to the ground versus the duration of the event of interest. And also, of course, the communication time between the spacecraft. There is also interest to do autonomy on board and collaboration on board when the information that is extracted from multiple spacecraft working collaboratively is smaller than all the full data sets, so it reduces the downlink requirements. Some basic conditions that we could identify are that the area of interest corresponding to the event of interest is observable by at least one spacecraft in the constellation at all time during the duration of the event of interest. Another condition is that the onboard processing time plus the inter-spacecraft communication time, and also what I didn't put there is the time to reconfigure or target the sensors is small compared to the change that happened during the event of interest. So an example is a transient event observation, and it can be a forest fires, it can be a solar eruption, or a volcano eruption. And the key capabilities here, as I said before, was first to recognize quickly and onboard the science event of interest, then exchange this data between spacecraft, take a decision of what needs to be done next, and then optimize the data acquisition by targeting the different sensors or the spacecraft, or reconfiguring the spacecraft, or either one spacecraft or several spacecraft. So these are the different questions for this particular example of the transient event observation, and I will not go through all of these. But what I want to go through a little bit is the technologies that are needed for this type of intelligent and collaborative constellation. And they can be categorized in four different classes. The onboard processing, and we heard about the high-performance space computing. Then there is a trade between do we really need radiation hardened versus radiation mitigation by software, like for the Space Cube. And one thing that Senga mentioned this morning is a neuromorphic computing that for machine learning algorithm can be very effective. The second part is the enabling and supporting technology. And among all these different technologies that we didn't talk about, one thing that is important is a semantic representation, or sometimes called the semantic bridge of the disparate observational data. So it's really having some representation of the sensors and of the data that are given by the sensor that can be easily exchanged and understood by the different spacecraft and fused and integrated. And I think that we probably talked about everything else, so I can leave it right there.
Okay. Thank you very much. John Bresina is up next. Can we have 7B, please?
Well, afternoon, I'm John Bresina from Ames here. And I was going to present this technology on Mixed Initiative Planner that deals with both activity planning and traverse planning. So if you have a mission with any kind of robotic rover type surface operations, you need to do both plan traverses for the rover and plan the activities that the rover is going to carry out. So typically this has been done by separate people, separate tools, fairly independently. So on MER, which I was a tactical activity planner, I was doing the activity plan while the rover drivers were doing the traverse plan. They just told me when the drive was going to start and how long it was going to take. And that would get updated as they did their sequencing, and I'd have to adjust the activity plan to accommodate for that updated duration. So that worked fairly well. MSL, I believe, is a very similar process. But a mission like Resource Prospector needs to integrate those two types of planning activities a little tighter than that, I believe. And part of the reason for that is temporal spatial constraints that they have to deal with, such as they have to stay in the sunlight for solar power and stay within direct line to Earth for pretty much constant COM. So they need constant sun pretty much and constant COM. So in the MER and MSL case, the activity plan and the traverse plan didn't really affect each other that much, other than some mutual exclusion flight rules, things that you couldn't do while you were driving, basically. However, for a mission like Resource Prospector, and this would correspond also to the similar mission on Mercury, where you're also, if you do solar power, it would be a similar thing. So here, to stay in the sun, how long you take to do your activities is going to affect when you leave a particular science station, and that's going to impact those constraints on staying in the sun. And the traverse plan, likewise, is going to limit how long you have to do activities, drilling and analysis at a particular station. So they're very tightly interactive and affect each other. So your activity plan and traverse plan do interact quite a bit, and you can't plan them independently. So we're looking at such missions and planning, and right now we're doing a prototype system that uses two legacy systems that exist already. One is OpenSPIFFE, which is based on what we used in MER and what's being used on MSL. It's a similar type of planner for activity planning. And this particular system includes this powerful constraint reasoning system called Europa. And then we're also using a traverse planner, starting with a traverse planner that was developed here at Ames for various analog missions and field tests called XGDS. And we've enhanced that to deal with these temporal spatial constraints with some reachability analysis tools, because XGDS was initially sort of an editor that a human would use without much automation. And to do this kind of planning, it's very hard to do without some help. So we added some capability to determine all the locations you can access safely from a particular location based on all these constraints. In addition, slope, but to stay in sun, stay in calm. This will tell you where you can go next. Then we also have another tool that tells you how long can you stay at a station, what's the earliest you can get to a particular location, and how long can you stay there, what's the latest you can depart from there. That gives you some sense of the flexibility and robustness of your plan, because things never go exactly how you planned. And then the third tool that we added to XGDS is a tool to generate automatically paths between two different science locations where you want to do some kind of analysis rather than having to figure that out manually. So that's all I wanted to say on this one slide. So we're looking at the sort of research issues of this. We're not part of the team, but we're trying to give them some advice as to how they can plan their activities and traverses in an integrated fashion. Thanks.
Thanks, John. Next up will be Butler Hine talking about reactive science. Do you want a laser pointer?
I just have the one chart. Terry asked for something that was that could sponsor or prompt discussions about what could be possible if you had a certain capability. So this one is reactive science decision making. We know that as missions get more complex, get closer to surfaces, touch surfaces, get to places with a lot of complexity, especially in harsh environments, we know that local decision making is going to be more and more important. So the context for this is the situation where ground control is unavailable, either from comm outages, limited bandwidth, just the decision time on the ground. Any of those will drive the response time. And if the science phenomena that you're trying to measure has a time scale more rapid than that, then you have to close the loop on board somehow. So that's the context. Extreme dynamic environments, we've heard over and over again today about some of the extreme environments that are driving this stuff. High radiation environments, transient phenomena. Jacqueline mentioned transient phenomena in the Earth case, but we also have transient phenomena in the outer planets cases. And then high operational complexity, where you're trying to coordinate a lot of different things, a lot of moving parts. You've got, you need dynamic replanning, reconfiguration, multiple vehicles. We've heard a lot of concepts about swarms. We've heard some things about multiple vehicles that have to be coordinated. That's the context for why you need local decision making. The classic example that actually was driving a lot of this thinking was a Europa flyby mission. We were looking at a secondary mission that could fly with a clipper and then fly through a plume and take science measurements. It turns out to be very challenging, as you might guess, but it really drove a lot of the need for local decision making. So the autonomy capability that is needed to address this, if you bring it down to from autonomy writ large to what is the specific thing that you need to do this type of address this type of mission need, is you need to process sensor data to identify and short-term predict dynamic phenomena. And this is not the way we do it now, which is we have onboard sequences that are executing on clock ticks, bang, bang, bang. Sometimes we'll have the complexity of a conditional where if you see this, then take this branch or that branch. We have that capability, but what we don't yet have, and maybe Earth observing is the closest thing we have to it right now, we don't have the ability to run a science model on board the spacecraft and then make decisions based on what the sensed data folded into the science model is telling us to do. So we don't have that capability, but that's what we mean by process sensor data to identify and predict short-term short-term predict dynamic phenomena. And then once you have that detection, adjust the mission plan to accommodate the transient phenomena that you think is coming or that you've detected. Adjusting the mission plan means that you then command maneuvers or instrument modes to achieve the new plan. And during all of this, you need to ensure fail-safe operations. And fail-safe is not what we typically do now, which is safe mode. Safe mode is an approach that makes you passively safe. But in these dynamic extreme environments, you can't often stop. You can't stop what you're doing. You need to fail active. You need to fail in an active way. And I have a concrete example of what drives this kind of thing, which is that Europa flyby. So what we were trying to do is stay on the clipper as it orbits, and then at some point, when you see a plume, let go, fly through the plume, take the sample. It turns out that requires, because of the light travel time and the decision time frame on the ground, requires a lot of decision making be done local. And what was driving it were two cases. One was detecting a plume. It's not a predictable event, so you don't want to take your shot and then fly through nothing. You want to fly through the plume you detect. But the other thing was, because of the command loop time and planetary protection issues, if you have a bad maneuver, you have to recover from that maneuver in a way that you do not impact the surface of the moon because of planetary protection. So you need to respond to anomalies, take onboard decision to do another maneuver, which is really tough sell for a project, but you need to do another maneuver not only to attempt to recover the science, but also to prevent yourself from impacting the moon and then violating your planetary protection requirements. So that's the example. So the thing to spark the discussion is, if you had this capability, what class of missions could you enable in the future? Okay.
Thanks, Butler. Next will be Uland Wong. This is 7D, I think it is.
All right, hello everybody. I'm Uland here at Ames Research Center. I work on robot perception, basically developing next-gen technologies to let robots see in the most extreme environments. And I'm going to do something controversial here and advocate for perception as a particularly critical component of autonomy. So if you remember Martin's slide from this morning, he had that flow chart of autonomy. Well, sensing and perception were the first boxes there. So I'll argue that without robust sensing and perception, we have no autonomy, not even little bits of it. So that's very important for robots that we want to operate on the surfaces of other bodies. Stereo vision is the tried and true method right now. It's the primary way that we see in 3D and operate robots on other planets, which has so far been Mars. I will note that the first generation of the Mars rovers did use some structured light, but that's no longer used. So let's think about what kind of perception we might need to explore other environments that, are very different from Earth and Mars, right? Unexplored worlds. So these can be environments like icy worlds that may have specular, very shiny materials. They may be planar features from orbit, but once you get to the surface, you have very complex vertical hazards like these penitente fields that are theorized to exist. Think about ocean worlds where robots are immersed in scattering media, and it's totally dark, so you got to bring your own lights, but you're in the fluid. And how are we going to be able to sense where we are or do science? Locate the rover or the samples, right? Are techniques from Earth enough to meet those challenges? Plumes and thick atmospheres, weather. How often would robots encounter things like rain or snowstorms or smoke and fire? Thick gas that obscures cameras. We have airless bodies, which are high dynamic range environments. So there's really high contrast between directly lit and permanently or totally dark shadows because there's no atmosphere to scatter the light. And finally, think about explorations of pits, caves, and tubes, right? Totally dark environments without any sunlight at all. And in addition, they may have confined geometry where depths of field and working distances play into your sensors. So how might camera-based vision that we currently use be augmented or substituted with some of the stuff that academia and other research labs are developing? And most of this list is a homework list. You can go figure it out by yourself, but I will mention some technologies that might be game-changing that you guys can think about. Micro LiDAR. Imagine not just a LiDAR small enough to fit in your hand, but small enough to fit in the drone that fits in your hand, right? Time-of-flight cameras. Some people's kids might play with the Kinect, right? How does a sensor like that, how would that change the missions that we have in mind? There are sensors that reject ambient sunlight in non-traditional manner using global illumination, and they basically use the flaw of rolling shutter cameras in order to be able to collect light from points where it's most important. There's sensors in development like compressive sensing that turn single point detectors into aerial detectors using statistical transformations. All sorts of other things, thermal and multispectral stereo. We don't have to do stereo vision with visible light. We can use thermal for areas where they may not be features like glacial surfaces, things like that. And think about how this stuff can benefit science as well, right? If we have these 3D models, can we use them to geo-register science data? And what sorts of data are actually conducive to autonomy, right? We may have a dense point cloud, but maybe there is a sparse point cloud with better data distribution that actually helps robots in confined spaces, for example. And I see Terry up there, so I'll end it at that. Thanks.
Thank you, Uland. And the last technology presentation is by Brian Coltin. Ricky, if you can get 7E up. Do you need a laser pointer? No.
So I'm Brian Coltin. I work here at Ames with Terry and Uland in the Intelligent Robotics Group. So on Wednesday, some of you may have seen this news article, a very tragic story. There was a security robot which was patrolling in some building, and it was doing its patrol, and then it rolled into a pond and drowned itself. And that's the current state of robots. They can do a lot of things really well. They're getting better and better, but at some fundamental level, they're still unbelievably stupid. And my challenge is how do we move beyond that? And it's not just a security robot. Most robots are like this. I used to work in the robot soccer. You'd see robots do all kinds of crazy things, like they'd perfectly line up and kick the ball, only to shoot it into their own goal. Or they'd fall down, their leg would break. They'd keep trying to stand up over and over again and not realize that they didn't have a leg that worked. Things like that. And I think that part of the problem here is that we're we have two different communities which really need to integrate. On the one hand, we have this perception and estimation community, like Uland's work or localization, and the machine learning communities. These people, they may have these great algorithms which are getting better and better to perceive and sense the world, but they have outputs in probability distributions or in neural networks, these very complex representations that deal with uncertainty at some fundamental level. And on the other hand, the robots at a higher level need to operate with some high-level logic. They have to understand that, oh, maybe we don't know if we can walk here, so we shouldn't step in the pond. There's also, they need to do planning and scheduling to think about what they should do, or diagnostics or fault management to understand what's gone wrong. But what normally happens when we combine these two is we take some probability distribution, and we just take the mean, plan with the mean, and throw the rest out. So my question is, how do we systematically reason about uncertainty? How do we know what the robot doesn't know? How do we know that, oh, we don't know what this surface is, maybe it's dangerous to walk on it? Or how do we, when we think we know something, we're often turned up to be wrong? How do we learn that we're wrong, figure out when we're wrong, and change our mind? And then when we're wrong, how do we know why we're wrong? And then how do we fix it? And I took the question of what autonomy technology would you like to use as a space mission more as what's my wish list of autonomy. And this, I think, is what we need to think about. How do we reason under uncertainty in some systematic way so that we can understand not only what we know, but what we don't know? And I'd like to mention that previous people have mentioned this perceive, think, act. And we often think of it as a pipeline. We first perceive the world, then we think about the world, then we act on the world. I think this is the wrong way to think about it. It's more of a cycle. We perceive the world, we think about the world, we realize, oh, maybe we need to take some other sort of observation so that we can better understand what's going on and better plan. And same with action. We take an action, then we perceive again, then we think again. It's a cycle, not only a pipeline. So I'd like to challenge all the scientists to think not only about what autonomy can do for your missions, think about what are the limits of autonomy. And for the technologists to continue thinking about how do we reduce those limitations so we can get closer to more and more autonomy. And I don't want to scare people away from using autonomy. The robots do drive into the pond sometimes, but there's ways to better understand where the autonomy is successful, where it might not be successful, and to do things like put humans in the loop to avoid those bad situations. Thank you.
Thank you, Brian.